So let's go over this problem here from the quiz. So you're given two blocks, M1 and M2. Their masses are up here. And you're told that there's a force of 20 newtons applied on the bottom block. There's no friction between M1 and the ground, but there is friction between M2 and M1. And so we're given, for that surface, we're given the MS and the MK as 0.60 and 0.50. And what you're told to find is the force, the horizontal force that M2 applies on M1. And so let's try to unpack this one. So the first thing we do in a force problem is we like to draw our free body diagram. So let's isolate the two blocks, M1 and M2. And so the forces on M2, we'll start with those. Horizontally, there's going to be one force, which I'll call the force of friction. And so that's the one that we're going to be dealing with, to try to unpack the most. And so that's the horizontal force. Again, it's going to be directed towards the positive direction over there. So we'll kind of do our usual XY axis like this. Now, other forces on this, there'd be what I'll call force normal 1, and then there'd be M2G of gravity pulling down. So those are the forces on the top block. On the second block, we're going to have, first of all, this thing that we're calling just F, which is, again, 20 newtons in this problem. Now, there would be a force of friction applied from the top block to the bottom one. And so what I'm going to do is whenever we have a sort of force like this, so these are Newton's third law forces. So whatever the force of friction on the top block is, the force of friction on the bottom has to be equal and opposite, just like our picture describes. Now, there will also be what we'll call a force normal 1 of M2 pressing down on M1. And that one as well is going to be a Newton's third law. So these two forces here should be equal and opposite as well. Now, to round out the forces, there's going to be what I'll call the force normal 2 of the ground pressing up on M1, and then, as usual, M1G. So these are our forces, and again, the one that we're going to be really focused on is the force of friction on the top block, because that's essentially what we want to find. And so if we can find either the force of friction on the top block or the force of friction on the bottom block, which again is equal and opposite, but we need to find it one way, in this particular case, to move forward. So as usual, with a problem like this, there's lots of ways to go forward. So what I'd like to do is look here, and let's calculate the force max of static friction for our particular case. And so that is the coefficient of static friction times the force normal, which in this case would be Fn1. Now if we look at block M2 and I do my Newton's laws, in the y direction I get Fy equals to 0, and so we'll get the situation which happens often, which is the force normal 1 will equal M2 times G. And so in this case here, we get mu s m2g, and when I plug that in, so again, mu s was 0.6, this is 2 kilograms, and g, I got about 11.8 newtons. Now let's go ahead and change colors there, and then we can also talk about the force of kinetic friction. And so it's just good to kind of go through, that's a similar equation, Fn1, but of course Fn1 we know is again this m2g. And this one will be a little bit less because the coefficient of friction now is 0.5. And so for that one, I got 9.8 newtons. Now what I'd like to do is just kind of go through and kind of discuss, because basically what happens is this force F here, whatever force is applied, that's going to determine which one of these sort of friction forces will be the most appropriate. And of course, this is just the static friction max. And so what I wanted to do is kind of just sort of unpack this a little bit and hopefully relate it to some of the stuff we know about static friction. So first, let's look at this thing here. So let's just assume, okay, that the force of static friction maximum is what the force is. Okay, and so that's the only force in the horizontal direction on M2. And so if I look at that then, in this particular case, if I sort of isolate block 2 and say that Fx equals m2 times a, so the only force acting on it would be the 11.a, so that would be the net force. And so if I solve for that acceleration, I'll get the Fx force divided by m2 which in this case would be 11.8 newtons divided by 2 kilograms, which when I calculate that out, I got 2.85, 5.9 meters per second squared. Now, what we're going to do, just, again, to sort of help clarify this, is we'll look at this a few times. So again, this is like block 2, this is block 1. So this force here. And so assuming that the two blocks stay together, okay, which is what we get here. So if this is the maximum static friction, then these two blocks are moving together, they're accelerating together with an acceleration of 5.9. And so then if I was to do F equals ma, so now this is the mass total. So this is sort of looking at the total mass. Then what that would give us, so I'd put in the total mass, which is 7 kilograms, times that acceleration of 5.9 meters per second squared, and that force I get to be 41.3 newtons. All right, so what that means is these two blocks will stick together, okay, and they won't move relative to each other all the way up to an applied force from the side. Because again, if I'm looking at these two guys together, the only force acting in the horizontal direction is the force F. And so that 41.3 is that force F. So one thing that is kind of interesting to try to do is to make a plot here. Again, to kind of just understand the broader picture of here. And what I'm going to do is I'm going to make the plot of force of friction acting on the block versus the applied force F. And so we just found, and so we'll measure, of course, both of these to be in newtons. And so we just found that right here, so this is 41.3. So at 41.3 newtons, we can go over here and say that what happens is that gives us our maximum static frictional force, which we again said was 11.8. And of course, the newtons are split up here. And so now what happens is at that point, this plot would look like this here. So above that 41.3, we would then be in the regime of kinetic friction, which would be 9.8 newtons, like this. At that particular point, the frictional force would be 11.8, and then what happens is we get something kind of like this here, a nice steady, and of course that should have hit this point here. We'll show you see how close we can get. So this will be what this looks like here. And so for anything less than 41.3, it's going to be, you can find it here on this particular plot here. And so we'll go through and kind of figure out how to do that here. But what we can hopefully see now is that since our force is 20, right, we're going to be somewhere in this regime here. And so our force should be less than the 41.3. Or I'm sorry, so over here we can just sort of write this over here and say our frictional force will be less than this 11.8. And then we got to figure out exactly relative to this 9.8, but we can kind of get a sense of sort of what's going on with that now. And so what we can now do is say, okay, so let's go back to this idea of thinking about the two blocks as one object. This is block 1, block 2. And so now I'll just do the same thing. So I apply 20 Newton force on this thing here. And so if I do my Newton's second law for this guy, I can go through and solve what that acceleration would be. And so here again, the total force is in the fx direction. So this would be like our sum of the net force divided by mass total. So in this case, it would be 20 newtons divided by 7 kilograms, which when I did this, I got a number of 2.85 meters per second squared. So that's the actual acceleration of these blocks. And again, since this is less than that number of 5.9, this is totally allowed. So we're definitely in the regime of where static friction is the one doing the friction. However, it's just going to be less than the maximum. So again, lots of ways to do these problems, but the way I would do it now is say the sum of the forces in the x direction equals ma for just block 2. And hopefully you remember from our diagram that the only force acting in the x direction was the force of friction, and I'll even be more clear and say this is the force of static friction, and it's going to equal m2 times a. And so this is 2 kilograms times 2.85 meters per second squared, and so when I multiplied that out, I get this number of 5.7 newtons. So if we go back over to here, then what we're saying is, so this 20 Newton mark gives us a value of 5.7. And so again, we're in this regime here where it's definitely static friction, but remember, this is the maximum static friction, and static friction will basically, push as much as you need it to up until that maximum point. And so in this case here, it only needs to accelerate to the 2.85, so you only need the total force of 5.7 newtons. So hope that helps. Let us know if you have any questions. Thanks.